So my name's Laura Peticolis, and I was an advisor for Andre, and we started working in January together. We've gone from the very small to the medium scale, and now we're going to go to the very large, looking at the sun, which has a diameter of 109, bigger than the diameter of Earth. So Andre looked at some of the plasma dynamics and images that were taken, and he'll tell you all about that next. It's been a great pleasure working with him. Andre Bernard.
Thank you very much. Andre. Let me figure out how to get this on. That'll work.
It's just
It doesn't. Yeah, you still have to project.
Yeah, I will. I don't think I know how not to. All right, so I worked on the Eclipse mega movie project with Laura Peticolis, having just introduced me. And to start off, this is an image used for the project, and we have the logo in the top right, right there. I thought they were nice touches, wanted to point them out early on. So eclipses, we've been interested in this for the history of humanity. People have drawn on cave walls, they've told stories. This is a quick simulation of how the sun casts a shadow using the moon and actually blocks out the light for a certain portion of the Earth. That's what's causing an eclipse, is the shadow of the moon between us and the sun. Now, here's an example of how interested we've been. This is an example of drawings done of an eclipse over Spain in 1860. And this is kind of the preliminary version of what we did with the Mega Movie project. This is a bunch of different people having drawn the corona, which is basically this aura of plasma in the atmosphere of the sun, starting about at the surface and goes thousands of kilometers off the surface. And the structures that you see when you have the moon covering the sun come out, and they change over time. So as these images are being drawn at different places, we're seeing different structures. And that's kind of what we're trying to take a look at with the movie. So here is a short video that shows the moment of totality, where the moon is perfectly over the sun and you now have complete obscurity of the sun, which allows the corona to be shown, as well as certain solar features like prominences. So this is what happens at totality. Now, if you are not at totality, if you have 1% of the sun showing, it's about 10,000 times brighter, and you lose access to a lot of these kind of features. So totality is extremely important in this kind of research. These are some of the coronal features that we are looking at during these moments of totality. Is we have flares, prominences, coronal mass ejections, and coronal jets. And this is just taken in different wavelengths at the same moment. And if you can see here on the top right, that's the approximate size of Earth compared to a prominence on the surface of the sun. Now this is a short video. Oh, I would like to warn anyone, if you're epileptic, this does flash a little bit, so I would recommend just looking away for a moment. So you're going to see in a moment right here, a solar flare is going to erupt, and it's actually going to disrupt the camera taking the image. So they're extremely bright, extremely powerful features on the surface of the sun. The next one here shows coronal mass ejections blasting off. This here is the actual, it outlines the sun itself, and this is basically a coronagraph, and it allows us to block off the greatest source of the light so that we can see the fainter features in these outer parts. They can be attached to telescopes and other kind of like satellite technologies to allow us to observe the sun in different ways. So I took a unique focus on coronal jets, one of the features, and you can see them here bracketed. They're basically collimated plasma jets coming off the sun due to a magnetic dipole on the surface. And they're collimated basically by something called the Lorentz force. And that you see here, with the force is equal to the charge of a particle, the velocity so the direction and the speed, as well as the magnetic field line that controls where these are going. These here are plasma traveling down open magnetic field lines of the sun. So these actually extend far out and will eventually reconnect, but it's such a large area that we call them open field lines. So what happens is basically the magnetic dipole creates a road, and then the direction that the particle is moving decides how it goes along that road. So if a particle is moving in the same direction as the magnetic field line, it experiences no force. It's going to keep going the same way it's been going. If it's going perfectly perpendicular to the magnetic field line, it's going to spin around that in the same, basically the same spot. It's just going to start spinning. Now if it's at an angle like this, it's going to spiral up and out along that magnetic field line. It's going to spin like the perpendicular, but it's also going to retain that vertical velocity, and it's going to spiral up and out, and it collimates the structure. So how do we look more at these, find out more about these structures and these features? The biggest problem about eclipses is that we get totality for about 2 to 3 minutes. How do we find more? And these two men, Hugh Hudson and Scott McIntosh, who later brought in Laura Peticolas, figured out that you can extend the period that we can observe it into about a 90-minute video by using images from all these different locations of this one eclipse. You stitch them together and use each image as a frame in the movie. So they did outreach, and they went to all these different campuses, press, publicity. They collected all these volunteers, and they trained them using, so you can take images with your phone or DSLR cameras, but there were training sessions for all these volunteers, and they got about 1,400 volunteers that eventually went out and did this, collecting about 50,000 images along this path of the 2017 North American eclipse. And you can see here, as you get farther away from that line of totality, you're losing more and more coverage of the sun. And like I said, if you have 1% missing, it's about 10,000 times brighter. So you need to be in this band. They collected about 1,200 images, 50,000 images, 1,200 of which were viable to be archived, equating to a huge collection of data. Now, Google actually got involved at this point to start developing algorithms to help collect these images so people could start sending them in. With all of Google's resources, they could not find enough coherent chronological images to test their own algorithm. So until this data set existed, they couldn't even test their own algorithms. That absolutely makes this the largest viable data set of an eclipse ever made by man. So this is an example using the NASA data that I showed you in the video earlier, what the Eclipse megamovie is trying to do. There's a huge portion here that we are not seeing in a lot of data. A lot of different data sets show small portions right around the sun and farther out, and there's a gap. We're trying to fill that gap. So you can see all these features here, and we're going to build a ton of images, stitch them together, and create a 90-minute movie that shows these areas. Now, to get into what I did while I was in the part of the team. It's a very big group of people, so I only did select jobs and tested out some of the code. But I started with the DS9 enhanced images. So DS9 is a computer program that allows you to change the way images look in terms of the way the light is projected. So you can see here, these are the same image, these are the same image, just done slightly differently. I changed some of the settings, changed the way they look, so you can see a little bit more feature here, a little bit more feature there. Basically, you just get them so you can get some of the crispness out, and that's where we start. And I took this one here so you can see that taking one of these images and boiling it down basically and reducing the brightness, you can see some of the features starting to come out right on the surface. So I started with that. I took the enhanced image and I put it into another computer program written in a coding language called Python. This program basically, it orients the image. So if I go back 2 slides, you'll notice these features line up. That is not by accident. It was extremely hard to do, actually. So when people started developing code for this, the goal was we need a few anchor points, and we need to figure out how to size and reorient the image. How do we do that? First off, the program looks for the outline of the sun here, or moon, I guess it's technically both. And it locates this circle, and we can now map this. This is our first anchor point. Our second anchor point is the team was lucky enough to have a star known as Regulus be bright enough and close enough to the sun at the time to be able to see. You probably can't see it, but there's a pixel here basically, a couple pixels lit up. That is Regulus. That is the star Regulus, and when it's done like this, you can see that where it's IDing the pixels. That is our second anchor point. Now, you have a center anchor point and a second anchor point that you can now normalize the distance here. So it's the same distance, that scales your image. Then if this pixel is in the center of the image and this is in the same pixel location, in every image, they're all the same size and they're all the same rotation. And that is how you get stuff like this, how you can line these up. Now we need to do that because obviously we had 1,400 volunteers taking images from different angles, different locations. There's all sorts of different issues that could come up. So this is extremely important coding. And this is a final image with the location of the star and further information. That's where what I did ended for this project. This is not my image, but it is another step that we would need to take. So you take the image and you see these it's almost like sand under the water. Basically, those are aberrations and imperfections in each of the different lenses. Everyone's taking this with a different camera. All these lenses have small problems here and there. When you compile them, you get a ton of issues. We can use code to basically smooth that out, and suddenly you're looking at really nice detail. And that's basically the goal of what we're trying to do with the code. And this is a final image. It's being updated all the time. But this is stitched together from a few hundred or 1,000 images, and you can see it's slow, but you can see the red dots appearing as the location of the image changes. So this is showing you in time where this image is taken, how we're stitching it together. And that is essentially the Mega Movie project. And then this is just going to get more detailed and more refined over time as we develop more and more code. For future work, I mean, it's huge. This isn't a project based in, we want to find out this. It's a project in, let's make a data set for people to study from. So we can figure out a ton, but really, I mean, this is a global project. Everyone now went from having 2 to 3 minutes of an eclipse to observe, that once this is refined, they're going to have 90 minutes of a single eclipse to observe. They're going to see these structures change over that period of time. And I'm very excited to see what comes out of it. We can see everything from internal structures cycles, external structures with the solar atmosphere. We can see propagation of solar wind and how it moves through the interstellar to the interstellar medium, and temperature inconsistencies. We see a lot of temperature inconsistencies in the atmosphere of the sun. A lot of people are wondering why. We have no good answer yet. So those are some of the future pieces of work, and I'm sure people much smarter than me are going to figure out way cooler things beyond this. And that is the Mega Movie project. And for anyone interested, I do have references and everything after that.
Questions for Andre?
So you had a slide with solar flares and CMEs and I'm old and I don't remember.
No worries, no worries.
Yeah, the coronal mass ejections and coronal. So what's the difference between those? Because to me, the coronal jets look like flares.
The jets? Okay, so the big thing is that the flare is this bright spot, effectively. It's this incredible release of energy and extremely luminous. The jets are an injection of plasma that, so in this image, again, warning for anyone epileptic, you'll see that it never jettisons off in a collimated structure. It becomes this extremely bright flare, whereas in this we have a steady collimated structure that, I mean, it changes, but it's not going to burst into existence and just fade. It becomes destabilized in different forms, and this plasma is continuously being pumped out due to the changing magnetic field line. So this is a full structure that will continue.
Is that more like an Old Faithful geyser?
Yes, I guess that's a good way to put it. Yes. Versus just a very bright emission of energy. Any other questions? All right.
Well, with that, let's thank Andre.